Memory management. Memory management is the functionality of an operating system which handles or manages primary memory and moves processes back and forth between main memory and disk during execution. Memory management keeps track of each and every memory location regardless of either it is allocated to some process or it is free. It checks how many memory to be allocated to processes. It decides which process will get memory at what time. It tracks whenever some memory gets freed or allocated, and correspondingly it updates the status. Process address space. The process address space is the set of logical addresses that process references in its code. For example, when 32-bit addressingly is in use, addresses can range from 0 to 0 times 7. That is 2 to the highest 3 to the highest 31 possible numbers for a total theoretical size of 2 gigabytes. The operating system takes care of mapping the logical addresses to physical addresses at the time of memory allocation to the program. There are three types of addresses used in program before and after memory is allocated. Number one is symbolic addresses. The addresses used in source code. The variable names, constants, and instruction labels are the basic elements of symbolic address. Next is relative addresses. At the time of compilation, a compiler converts symbolic addresses into relative addresses. Physical addresses. The loader generates these addresses of the time when a program is loaded into main memory. Virtual and physical addresses are the same in compile time and load time address binding scheme. Virtual and physical addresses differ in execution time address binding scheme. The set of all logical addresses generated by a program is referred to as a logical address space. The set of all physical addresses corresponding to these logical addresses is referred to as a physical address space. The runtime mapping from virtual to physical address is done by the memory management unit, which is hardware device. MMU uses following mechanism to convert virtual address to physical address. The value in the base register is added to every address generated by a user process, which is treated as offset at time it is sent to memory. For example, if the base register value is 10000, then an attempt by the user to use address location 100 will be dynamically reallocated to location 10100. The user program deals with virtual addresses. It never sees the real physical addresses. Static versus dynamic loading. The choice between static or dynamic loading is to be made at the time of computer programming being developed. If you have to load your program statically, then at the time of compilation, the complete programs will be compiled and linked without leaving any external program or module dependency. The linker combines the object program with other necessary object modules into an absolute program, which also includes logical addresses. If you are writing a dynamically loaded program, then your compiler will compile the program, and for all the modules which you want to include dynamically, only references will be provided and the rest of the work will be done at the time of execution. At the time of loading, with the static loading, the absolute program or the data is loaded into memory in order for execution to start. If you are using dynamic loading, the dynamic routines of the library are stored on a disk in a relocatable form and are loaded into memory only when they are needed by the program. Static versus dynamic linking. As explained above, when static linking is used, the linker combines all other modules needed by a program into a single executable program to avoid runtime dependency. When dynamic linking is used, it is not required to link the actual module or library with the program. Rather, a reference to the dynamic module is provided at the time of compilation and linking. Dynamic link libraries or DLL is in Windows, and shared objects in Unix are a good example of dynamic libraries. Swapping. Swapping is a mechanism in which a process can be swapped temporarily out of main memory or moved to secondary storage disk and make that memory available to other processes. At some later time, the system swaps back the process from the secondary storage to main memory. The performance is usually affected by swapping process, but it helps in running multiple and big processes in parallel, and that's the reason swapping is also known as a technique for memory compilation. The total time taken by swapping process includes the time it takes a move to enter process to secondary disk and then to copy the process back to memory, as well as the time the process takes to regain main memory. Let us assume that the user process is of size 2048 KB and on a standard hard disk where swapping will take place has a data transfer rate around 1 MB per second. The actual transfer of the 1000 K process to or from memory will take. Now considering in and out of time, it will take a complete 4000 milliseconds plus other overhead where the process competes to regain main memory. Memory allocation. Main memory usually has two partitions. These are the low memory and the high memory. Low memory operating system reside in this memory. High memory user process are held in high memory. Operating system uses the following memory allocation mechanism. Single partition allocation. In this type of allocation, relocation register scheme is used to protect user process from each other and from changing operating system code and data. Relocation register contains value as small as physical address, whereas limit register contains range of logical addresses. Each logical addresses must be less than the limit register. Multiple partition allocation. In this type of allocation, main memory is divided into a number of fixed size partitions, which each partition should contain only one process. When a partition is free, a process is selected from the input queue and is loaded into pre-partition. When the process terminates, the partition becomes available for other process. Fragmentation. As processes are loaded and removed from memory, the free memory space is broken into little pieces. It happens up to sometimes that processes cannot be allocated to memory blocks considering their small size and memory blocks remain unused. This problem is known as fragmentation. Fragmentation has its two types. One is external fragmentation. The total memory space is enough to satisfy a request or to reside a process in it, but is not contiguous, so it cannot be used. Second one is internal fragmentation. Memory block assigned to process is bigger. Some portion of memory is left unused, as it cannot be used by another process. The following diagram shows how fragmentation can cause waste of memory, and a compact technique can be used to create more free memory out of fragmentation. External fragmentation can be reduced by compaction or shuffle memory contents to place all free memory together in one large block. To make compaction feasible, relocation should be dynamic. The internal fragmentation can be reduced by effectively assigning the smallest partition but large enough for the process. Paging. A computer can address more memory than the amount physically installed on the system. This extra memory is actually called virtual memory, and it is a section of a hard that's set up to emulate the computer's RAM. Paging technique plays an important role in implementing virtual memory. Paging is a memory management technique in which process address space is broken into blocks of the same called pages. Size is power of 2 between 512 bytes and 8,192 bytes. The size of the process is measured in the number of pages. Similarly, main memory is divided into small fixed-size blocks of physical memory called frames, and the size of a frame is kept and the same as of a page to have optimum utilization of the main memory and to avoid external fragmentation. Address translation. Page address is called logical address and presented by page number and the offset. Frame address is called physical address and represented by a frame number and the offset. A data structure called page map table is used to keep track of the relation between a page of a process to a frame in physical memory. When the system allocates a frame to any page, in translate this logical address into physical address and create entry to the page table to be used throughout execution of the program. When a process is to be executed, its corresponding pages are loaded into any available memory frames. Suppose you have a program of 8 KB but your memory can accommodate only 5 KB at a given point in time, then the paging concept will come into picture. When a computer runs out of RAM, the operating system will move idle or unwanted pages of memory to secondary memory to free up RAM for another processes and brings them back when needed by the program. This process continues during the whole execution of program where the OS keeps removing the idle pages from the main memory and write them onto the secondary memory and bring them back when required by the program. Segmentation. Segmentation is a memory management technique in which each job is divided into several segments of different sizes, one for each module that contains pieces that perform related functions. Each segment is actually a different logical address space of the program. When a process is to be executed, its corresponding segmentation are loaded into non-contiguous memory, though every segment is loaded into a contiguous block of available memory. Segmentation memory management works very similar to paging, but their segments are of variable length, whereas in paging pages are of fixed size. A program segment contains the program's main function, utility function, data structures, and so on. The operating system maintains a segment map table for every process and a list of free memory blocks along with segment number. Their size and corresponding memory location is in main memory. For each segment, the table stores the starting address of the segment and the link of the segment. A reference to a memory location includes a value that identifies a segment and an offset.